Hi everybody, Happy New Year. I decided to start the year off in a good way and decided to make a video on January 1st. Um, Today's video is it's the first video. It's on my quantum field theory, a student's perspective course. And this is lesson 5.5, functional calculus and functional derivatives. Just noticed something interesting. What was fixed before on the daytime, it was finally fixed, and now it's broken again. Anyway, first of all, with respect to the numbering, what I'm doing in my course is lesson numbers follow the chapters or sections in Schrodinger's book. But I'm adding lessons on things that aren't covered in Schrodinger, and or they're covered later in spinors or in gauge theories. So I'm sort of adding some intermediate lessons. I've already added one on 3.5, so I'm going to use numberings of like decimals, like 3.5. I think I added on non-abelian, at least on a classical level, gauge theories. By the way, I should say version 2. And this lesson is going to be numbered 5.5, and it's on functional and calculus and functional derivatives. Schrodinger covers the path integral approach. As a matter of fact, he emphasizes it. But there's another approach, which is called the Schrodinger equation type of approach. And only one book covers it. It's completely different than the canonical or path integral approaches. So for this approach, it's definitely like functional calculus all the way. And so the reference here is chapter 9 of Hatfield. Field theory of point particles and strings. 2/3 of the book is on quantum field theory, and 1/3 is on strings. So let's start. I like to start with the definition of a functional. A functional is just an object. It's really just a function, but it's a little bit different. It maps functions to numbers. Usually complex numbers, but it could be real numbers as well, or I guess quaternions or something. So, and we denote functionals by square brackets. So if we have a, it's a function on, let's say, space, which has vectors, let's say x, and it maps to complex numbers. So this means that a of x, the function a evaluated at x, is in C, complex numbers. A functional of a, on the other hand, it maps the whole function to C. So, for example, you might have something like f of a. This is just one example. It's defined to be the integral from minus infinity. This is just one example. The integral from minus infinity to infinity of a of x dx. So whatever function we substitute for a, we're going to get a single, assuming convergence and some other issues, we're going to get a single number of it. So it maps the function a to a number. And you can have all kinds of examples. You could have f of a equal to the max of, let's say, x, an element of the domain of a of x. So this would just take any function and map it to its largest point or its minimum point, so on. This is functional. We take the whole function and we get a single number out of it. Now let's talk about functional derivatives. Now, nothing that I do and nothing anybody does in functional calculus is really very rigorous. They may try for a while, but it's very, very hard. But the definition that Hatfield gives, he says del f of the functional a with respect to a, and he defines this as the limit epsilon goes to 0 of f of a plus epsilon delta minus f of a divided by epsilon. So it's kind of like you have your function and you vary it at only one point. Like sometimes they put in like del a of x, so to emphasize that you're evaluating this at the point x. So here you would have the function a of x everywhere. Well, let's say a of y everywhere. And then at the point x, you would have a of y plus epsilon delta x minus y. That would be how you change the function a little bit. And then you apply that derivative. And this is used, in path integrals and everywhere in quantum field theory all the time. And it's easy to see. There's only one formula really that you need to remember. Everything else is just like regular calculus. But if you have something like del a of y, del a of x, this is equal to delta x minus y. So this is how it comes. This is what you have to remember. This is how it's applied all the time. And I'll give you an example right now. Let's say we have an action. We have an action, typical action in scalar quantum field theory, an interacting action. Our functional is the action of phi. Phi is the scalar field. I don't know why it does that. So let's say we have the integral of d4y partial mu phi of y partial mu phi of y. I won't always show the arguments, but they're obvious. Like if we're integrating with respect to y, then y is the argument of phi minus m squared phi of y squared. Usually we have this part times 1/2. And then we have minus, this is the interaction term, phi of y to the 4th. So this is the interaction. This would be known as like phi 4th theory. So the usual equations of motion and everything whether you use Euler, Lagrange, or whatever, is just del phi of x equals 0. So let's calculate this. This should be del S of phi. So I have del equal to the integral d4y minus 1/2. And now, the basic rule, you can do your integration by parts and everything, but the basic rule is that the derivatives, the functional derivatives, can go sort of commute with ordinary space-time derivatives. So you can go right through them. I mean, what you can do is you can do a partial derivative, integration by parts. I'll probably do the integration by parts anyway, yeah. So I'm going to write minus 1/2 del phi of x, and I'll write phi of y partial mu phi of y plus m squared. See the sign reversed between these two terms by the integration by parts. For this term, plus m squared phi of y squared plus lambda 4 factorial. It should be 4 factorial. Yeah, 4 factorial is 24. So I'm going to write it as, I took 1/2 out, so I'll just write it as lambda over 12 phi of y to the 4th. And now, basically, it's easier to just apply the functional derivative right to that term using the formula that I gave before, minus 1/2. Now I get del x minus y, partial mu phi of y. And now, of course, there's another phi. You could imagine, for this one, reversing both the partial derivatives, you'll get 2 of them. So you're going to get a half. But you're always going to get 2 factors. So it's as if you can just go right through these and just differentiate a product, each one. Plus phi of y, partial mu, del x minus y. And I'm going to put a arrow like this to indicate it's acting on that, because we did two partial derivatives there. And then the rest of it is just standard calculus. The derivative of like phi squared is going to be 2m squared phi of y del x minus y. And then I'm going to get plus lambda over 3, 4 times 1/12 is 1/3, phi of y to the cubed del x minus y. So we end up getting del s, del phi of x. After a while, a short while, you'll do all of these by hand, minus the partial mu phi of x, because when you do the delta integrations, it takes out the y variables, minus m squared phi of x minus lambda over 3 factorial phi of x cubed equals 0, or just getting rid of the minus signs here. So that's our equation, and the basic problem of quantum field theory is that this is a nonlinear equation and extremely difficult to solve. That's what makes quantum field theory so hard. Now I want to move on a little bit to the stuff that's more involved when we do. I'll have a separate lesson on the Schrodinger representation for scalar fields. The Schrodinger representation is sort of like, if you've taken quantum mechanics, you notice that we had a wave function, and the square of that gave the amplitude, the probability, amplitude squared gave the probability of something. And you notice in quantum field theory, we tend to do overlaps between states, but we don't seem to have a wave function. Well, you can do it with a wave function way. It's called the wave functional approach. And this is what Hatfield does. And to do the wave functional approach, you need to use functional differential equations, which is what I want to go over right now. Okay. So a typical I'll call it FDE that arises in QFT is the following. The integral of dy del a of y. I'm going to have two functional derivatives. Then this is the functional, the unknown functional f that we're trying to solve for, plus the integral dx dy. This is just an ordinary function, small f, f of x comma y, a of x, a of y, again multiplied by the functional. This is equal to like mu times the functional. And you'll see when we do the scalar theory that this arises equations like this. So that's why I'm solving this one. In this equation, we assume that the coupling f of x comma y, you can see f of x comma y couples fields, A's are fields at two different points, is symmetric. Now, since f of a appears in each term, notice there's an f, there's an f, and there's an f. It makes sense to try an exponential. So we try something like the functional of a is equal to some normalization constant times exponential g of a. Okay, I always do that, but since we're using functionals, it's best to only use square brackets for the actual functionals. And then try and solve for g of a. So substituting in the FDE, we're going to get, I'm going to do this because this is new for, I guess, most of you watching here. I'm going to do it painfully slowly. And Hatfield, by the way, has a lot of errors in his books. He has a lot of numerical factors that are off, factors of 2, negative signs, factors of I. They're obvious, so it just keeps you on your toes. Okay. So now this leads to the integral of dy del a of y. When we take the first functional derivative, it's an exponential, so the derivative of an exponential is just an exponential times the derivative of whatever inside that exponential. So we're going to get del a of y g of a times the exponential of g of a. And then the next term is the integral of dx dy f of x comma y ax ay exp. Notice the normalization constant canceled out, so that's just arbitrary. This is equal to mu exp g of a. Now, so let me just rewrite this. Just move something to the other side. Okay. And if you take another derivative, now if you take the second derivative here, when you apply it to the exponential, you're going to get the same thing again. So you're going to get g of a come down again. Well, let's first apply it to the first term. I have one derivative here. When I apply it to this derivative, I'm going to get g of a. And then I'm going to multiply by the exponential term. But the exponential term is going to cancel in all the factors, so I'm leaving that out. And then I get another term, which is, I take the derivative of this. I took that. I already have that. This term over here. And now when I take the derivative of the exponential, I get that again. So I get del a of y, g of a squared. And this is equal to mu. And now I'm just going to move the f term on the other side. U minus the integral of dx dy. And we canceled out the exponential from all the terms. F of x comma y. A of x, a of y. So this is the equation we have to solve right now. We have to solve it for g. And the easy way to do this most of the time is, we look at powers of a. So on the right-hand side, we have two terms. We have a term with 0 powers of a. That's the mu term. And a term with 2 powers of a. That's the minus f of x comma y term. So this tells us that we should try a quadratic functional. I'm going to use different letters here. And again, we assume G is symmetric, just like F was assumed symmetric. So the idea here is when we take one functional derivative, that's going to knock down 1 power of a. Then we're going to square it, we'll get 2 powers of a. That can take care of the f of x comma y term. When we take two functional derivatives of this, it will eliminate both of the a's and we'll get a constant term. So that should give us 2 equations to solve, and it does. So we get the integral of dy. I'm going to take one derivative term, del a of y. And now let's take the derivative of g using this g over here and here. Let's just take one derivative. What are we going to get? We're going to get the integral dw dz g of w comma z. And let's first differentiate the az term. We're going to get a of w, and then we're going to get del z minus y. And then there's another term because we have 2 a's. And after a while, you'll do this automatically, and you'll see that they're the same, especially since g is symmetric. Now we're going to get g of wz. We're going to get a of z del w minus y. Now, this part here, we're going to need this whole part, which is the first derivative, we're going to need in this term as well. So let me just simplify it. So this ends up being the integral dw g of w comma y a of w plus the integral dz g of y comma z a of z. But you can see they're the same if you just substitute z goes to w. It's the same because g is symmetric. So this is just equal to 2. I'm going to change the variable here, name anyway. 2 the integral of dx g x comma y ax. So now let's go back in our differential equation. So now I have to take another derivative of del a y of this. This is going to give me a delta function of x minus y, so I'm going to substitute in y. So my differential equation all the way back up here is going to be, I'm going to get 2 times the integral of dy. Remember, we had a dy all the way in front, and we haven't done anything with that. Now I'm going to have, when I evaluate this, after taking the functional derivative of that, I'm going to get 2 dy g of y comma y. This is the one with no powers, and this equals mu. So that's one of our equations that we need to solve for g. And the second equation, the more interesting one, I'm going to have this whole thing squared. So let's see what this whole term squared is going to be. I'm going to have a 4, the integral of dy. Now, since I'm writing this twice, I can't use the same variable x each time. So I'm going to have dx, and I'm going to use du the second time. So I'm going to have g of x comma y, and then a of x. And then for the second term, I'm going to have g of u comma y, and a of u. And this has to be equal to minus the integral dx dy f of x comma y ax ay. Okay, so the best thing here is just change variables. Change u go to y. Just rename the variables and y go to u. So we end up getting 4, the integral of du dx dy g of x comma u g of u, well, u is going to go to y is going to, but it's symmetric, so it doesn't really matter how I write it. G of u comma y. I should just do it, g of y g of y comma u a of x a of y is equal to minus the integral of dx dy f of x comma y a of x a of y. So we have these that line up nicely. We have the a of y that line up nicely. We have the integrals that line up nicely. So we just get our final equation is f of x comma y is equal to minus 4 times the integral of du g of x comma u G of y comma u. So these are our solutions. So we have to find functions. The first one is just any function of g, once you have mu, there's a lot of any normalizable function, you can always scale this so you'll satisfy that. So that really doesn't give us much. But then you need some kind of convolution of g that gives you f of x comma y. And that's a well-known problem. Okay. So next time I will cover functional integrals. We'll have one video on the bosonic case, real and complex, and one video on the fermionic, case, which involves Grassmann variables. And we'll do the real and complex case as well. The idea of complex Grassmann variables really sort of annoys me, but that's the best we can do. I'll hope to see you next time. I'll try and get these videos out as soon as I can, and thank you for watching.